Welcome to Unit 9, Lesson 2, Wave Properties Continued. The speed of a wave only depends on the media it travels in. For example, sound waves travel faster in water than in air. That's because the more dense the material is, the faster a wave can travel through it. Waves passing from one medium to another will have the same frequency, but may have different speeds. The frequency of a wave is always determined at the source that's generating the wave in the first place. Superposition is the displacement of a medium by two or more waves and is the algebraic sum of the wave's displacement. When waves interact this way, we call it interference. There are two forms of interference. The first is called constructive interference, where we simply add the amplitudes together. And the next is destructive interference, where we subtract the amplitudes. On the left-hand side, let's say we had a 1 meter high crest meeting another 1 meter high crest. We would have constructive interference, and we would add those two amplitudes together to produce a 2 meter high crest. On the right side, if we had a 1 meter high crest meeting a 1 meter low trough, those would cancel each other out and we would have a zero amplitude wave. A standing wave, also known as a stationary wave, is a wave that remains in a constant position. This phenomenon can occur as a result of interference between two waves traveling in opposite directions through a medium. The diagrams below show standing waves at various resonance frequencies, where a series of nodes and antinodes are produced. A node is a point in the medium that is not disturbed due to destructive interference, and an antinode is a point of maximum displacement due to constructive interference. The diagrams below show, let's say, a spring or a string being shaken at certain frequencies. The first is called the fundamental frequency, where if the rope is shaken a certain amount, there will be a node produced at the starting point, an antinode will be produced in the middle, and a node will be produced at the far end. The wave is being sent down the medium to the right and reflects back to the left, interacting with the next incoming wave. That would generate a resonance frequency, and you would get maximum displacement in the middle, followed by no motion or no movement at the ends. If we were to increase the source of the shaking on the left-hand side, send more waves down the string, we would get the same effect as above, except for we would produce more nodes and antinodes. In the first overtone, you'll see that we would generate one complete wavelength as the waves travel to the right and left and interact and interfere accordingly. On the left-hand side, you'll see that the nodes and antinodes are labeled. Nodes, antinodes, and so on. If we were to increase the shaking of the frequency to the second overtone, you'll see again the generation of more nodes and antinodes. In the last diagram here, you'll see there are exactly 1.5 wavelengths being generated. Again, the amplitudes will be in the middle, indicating maximum displacement, and the nodes will be where there's destructive interference and no motion. When a wave reaches a boundary, it bounces back. Ray diagrams are used to show the directions waves travel when they interact off of the surface of a boundary. The law of reflection states that the angle of incidence will always equal the angle of reflection. The normal is defined as 90 degrees to the surface, and it's important that when we use the law of reflection that we're always measuring the angles measured from the ray to the normal, and from the normal to the reflected ray. When plane or straight waves reflect off of a parabolic reflector, their direction changes so that they will reflect to the central area called the focus. The waves do not change speed nor wavelength, they only change shape from straight waves to circular waves. A common situation this is used is where we use parabolic microphones at sporting events so that we can hear things happening from a long distance away. Waves sent along fixed strings are inverted after reflection, and waves sent along free strings are upright after reflection. The left-hand side shows a wave pulse traveling down a string to a fixed end, and the reflected pulse is on the opposite side from which it came in on. On the right side, we see a free end where the wave pulse travels in on the top side of the string and is free to move, this end moves up and down and therefore reflects on the same side of the string on the way back. Refraction of a wave is the change in direction of the wave due to a change in the wave's speed as a result of the wave traveling from one medium to another. In this diagram we see deep water waves, which is a faster medium, traveling into shallow water, which is a slower medium. The wave will refract in such a manner that it will bend into the shallow medium. The reason for this is as the wave travels towards the top of the page, the waves that are reaching the shallow end will start to slow down. The waves in the deep water will continue traveling at the same speed, and because they're one continuous wave, they will not break, they will simply start to bend and change in that direction. When we travel from a faster medium to a slower medium, if we compare the angle of incidence, we'll see that it is greater than the angle of refraction. In other words, we say that waves are bent towards the normal when they slow down. If we look at the right side of the diagram, if we extend that normal, we'll see that that wave is actually bent towards the normal relative to the incident ray towards the normal of the surface that direction. In this case, the angle of refraction is smaller than the angle of incidence. The waves do not change their frequency, they just change their direction. As waves travel into the slower medium, you'll see the wavelengths start to decrease. The distance between the waves will start to get smaller because one wave will start to pile up on the next. Diffraction is the bending of a wave around an obstacle or through an opening. In this picture, we see plane waves that are traveling through a small opening. The waves on the very edges where they touch the barrier will start to slow down and therefore change their direction. We get a bending of a wave from plane waves into circular waves as waves travel through this little opening. To the right we see that the gap distance is increasing and therefore the amount of diffraction occurring decreases. The reason for this is the majority of the wave starts to travel straight through that opening without being affected whatsoever. It's only the edges, the very ends of that wave, that are slowed down by the barrier, and therefore a little bit of curling or a little bit of change in the shape of the wave occurs at the edges. The frequency nor the wavelength change. Sound waves are good examples of longitudinal waves. Air molecules move with areas of rarefaction and compression. The frequency of sound waves is the pitch. Higher frequency equals higher pitch, and lower frequency equals lower pitch. The loudness of a sound wave depends on its amplitude. The Doppler effect is the apparent change in a wave's frequency, or the pitch, the sound of it, resulting from the relative velocity between the source of the waves and the observer. For example, race cars are good examples of objects that can produce the Doppler effect. As they're traveling quickly to the right, sound waves pile up on the leading edge, and an observer in the front of the car will hear a higher pitch, and as the source or the car travels past an observer, they will have lower frequency sound waves and therefore hear a lower pitch. To see this in action, let's assume the red dot is our race car. The sound waves in front of the car would be piling up on each other, and the frequency of the sound would be a higher pitch in front of the car. Behind the car, the sound waves are spreading apart, and therefore it would sound as a lower pitch sound as the car traveled past you. That's why when you listen to a race car traveling past a certain spot on the racetrack, it sounds like this. Meow. A barrier wave is where an object moves at the speed of sound. On the leading edge is an area of extreme high pressure, followed by an area of extremely low pressure. There is an enormous pressure differential in the front and ends of that object. You'll see this again in this moving diagram here, an area of high pressure in the front, followed by low pressure behind. In order for humans to break the sound barrier in planes to go supersonic, we had to come up with engines that were strong enough and powerful enough to break through that area of high pressure. If we are to continue to accelerate the plane, if we can push it through that area of high pressure, we go what's called supersonic. If an object is to travel faster than the speed of sound, we see the shape of the cone behind the plane change into a three-dimensional Structure. This is where we would hear a sonic boom because of the extreme pressure differential in the front edge of the object to the rear of the object.